Assalamualaikum and good evening. Today our group would like to present about our assignment, which is about second order system in any engineering application. For our group, we choose the second order system in the application of rice cooker. Okay, rice cooker consists of main body and inner pot to hold the rice and water, and also the electric heating component and a thermostat to detect the temperature changes in the rice cooker. It has the ability to cook rice and turn down the heat when the rice is fully cooked to keep it warm without burning. After filling the pot with rice and water, it will be heated until the water reaches the boiling point temperature, which is 100 degrees Celsius. The temperature inside the rice cooker will raise above the boiling point when all the water is absorbed. And after that, the rice cooker will switch off by itself to enter the resting phase. Okay, now I will explain about the input, the output and the controller. For the input and the output of the system, adjust the SM unit step of the temperature in order for the rice to fully cook. And for the controller is a thermostat. The controller for the system is a thermostat which is for detecting temperature changes and maintaining the temperature inside the pot, inside the rice cooker. And then the limiter that we set for the rice to fully cook is 120 degrees Celsius. Okay, so now here is our transfer function. The value inside our project's transfer function are just an assumption. We just assume all the value. Okay, now I will pass the presentation to Hazwan.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hazwan Firdaus bin Muhammad Hazli. Okay, so first for the simulation for the system, as we can see here, the step input. So the step time is 0, initial time 0, final value is 1, sampling time 0.01, for the clock is 10 and the stop time is 1 second. Parameter step value is 40, 65, 120. So this will be for our input. Okay. Next, this is the simulating model for our system. Okay, so this is the transfer function as the thermostat. Okay, so now for the graph, for the table, for the input is 40, 65, 120. Okay, for the final value, we can see here the more increase of the input, so the final value also increase, and the peak value also is the same. Okay, for the overshoot percent, okay, as we can see for the percentage, it's barely the same, but for the input of 120 got the lesser percentage of overshoot, so that's mean input for 120 is more stable. Okay, for the TS, for the three inputs is same. Okay, so that's for the table, and now the graph for the 40 Celsius. The red line is our thermostat and the blue line is the step. Okay, we can see here for the 40 Celsius, and this one is for the 65 Celsius. Okay, and last one is the 120 input. Okay, so that's all for me for the simulation part.
Hello, my name is Nikato Anak William. Today I'm going to explain about our calculation part for our assignment. First is for the calculation part overshoot percentage, and how we calculate it is Cmax minus by C final over C final and multiply by 100, and then we get the percentage of the overshoot for 40, 65 and 120. And for the ESS, which is error, how we calculate it is take the input value and then we minus by the final value and we get the ESS. Number 3 is how we get the TS and how we calculate the TS. 0.9 multiplied by final value, and then we get the value here. So we get the value here, we need to move the cursor and we get the TS for 40, 65 and 120. And then we calculate the TR, which is 0.9 C final minus 0.1 C final. And after that, we move the board cursor 1, cursor 2, and then that value we take is value from delta t for both cursor. And then this is for the theory part, how we calculate the natural frequency, the blink time, the blink ratio, peak time, TP, settling time, TS, rise time, TR, then overshoot. So for the peak time, what we get here is 0.052, and what we get from the simulation is not big difference here. And for the TS, which is settling time, but we get 0.0 and 0.246 second, and we get from the simulation is 0.128 second. That also not a big difference. What is big difference here is the percent of overshoot. The percent of overshoot we calculate is 42.767%, and what we get from the simulation that we calculate it is only 21 point something, 21.86. And then this is for our state space representation, and then this is for the steady state error for KP, which is position constant, KV velocity constant, and KA acceleration constant. And for KP we get this value, and unit step input we get 0.6 milli, and unit ramp input we get 0.6 also milli, and only this KA we got 0, and the unit parabolic input we get infinity. Okay, that's all for me. Thank you.